Hello everyone, my name is Hu Yao. My name is Hu Yao. I'm the project researcher in National Institute of Informatics in Japan. Today my topic is about the case for unbounded lossy floating point data compression on interconnection networks. So this is the outline of my presentation. So first, this is the background of this paper. And we know that in parallel applications, the floating point data are frequently exchanged between the computer nodes. For some error-tolerant applications, the perfect precision or perfect communication is not necessary. So in most cases, the communication overheads have a side effect on the application performance, like execution time, and the network performance, like the scalability. So the solution is the data compression, which means we can allow some errors to substantially reduce the communication overhead. For example, from the 64-bit double precision values to shorter bit streams. And of course, there should be a trade-off between the compression speed and the quality. So in this study, we propose an unbounded lossy floating point data compression technique on interconnection networks. And existing data compression techniques usually target the storage systems. So to the best of our knowledge, this work is the first to apply the data compression technique to the interconnection networks, which are usually latency sensitive. So to improve the efficiency of the communication, the simplest method is to reduce the number of communication messages, but this will introduce non-negligible errors. So this is not the case for our use. So our solution is to use the compression. So compared to the lossless compression, the lossy compression usually has a higher compression ratio at the cost of the lower data precision after the data is decompressed. So our challenge is to realize both the high compression ratio and the relatively fast interconnection networks, and because usually the interconnection networks are latency sensitive. So in this case, we focus on obtaining a final output of quality by using a lossy runtime compression algorithm for floating point data. So in this work, we propose two lossy compression techniques. The first is a simple solution, which is called the bitewise compression scheme. And the second is a complicated solution, which is called the bitwise compression scheme. And both the methods use a versatile linear predictor. For the bitewise compression scheme, the data is compressed to 1 byte if the data is predictable. Otherwise, if the data cannot be predicted, it will not change anything. It just be transferred as it was. For the bitwise compression scheme, the data is compressed to 2 bits if the data is predictable. Otherwise, if the data cannot be predicted, we perform the bit routing and discard the least significant bits on data. So in this work, we also investigate the trade-off between the compression speed and the efficiency of the two compression schemes. So first, I will introduce the bitewise compression scheme. As mentioned earlier, it uses a versatile linear predictor, like in some famous works. And in this case, we can predict the data by its preceding elements within the error bound. For example, we can get the in this figure, we can see that we can get different predictions by using these formulations. And here D is the real value and P is the prediction of the value D. So we can see in this case, the P3 can be used as the right prediction of the data D because the prediction is within the error bound. So in this case, we say that the prediction succeeds. And in this case, we can see any prediction is outside the error bound. So we say that the prediction fails. And this is the algorithm of the bitwise compression scheme. So we should notice that before the linear prediction, we convert the input data set into non-negative floating point data. And this is to flip the sign bits of the negative values to 0 for the purpose of lossy compression. And here we use 1 byte to express each linear prediction. And theoretically, 1 byte can express 256 predictions at maximum. And in practice, we use the first 4 predictions considering the overhead. And later in the evaluation, we can see the first 4 predictions are enough to conduct the data compression. And at the encoding phase, we insert the displacement information to differentiate the compressed data and the uncompressed data. And this is the MPI implementation of the bitwise compression scheme. And the left is the point-to-point communication, and the right is the collective communication. And here we use the basic functions and basic data types for high portability to different MPI implementations. For example, we use MPI int to encapsulate the displacement information and use MPI char to encapsulate the compressed data. And the uncompressed data will be encapsulated in MPI float or MPI double. So this is for the purpose of high portability. Next, I will introduce the bitwise compression scheme. And here the linear predictor is similar to that in the bitwise compression. And the difference is we use the bit routing if the data cannot be predicted. And here we know, and this is the binary expression of the floating point data. And here the point is we must calculate how many bits are necessary and how many bits are not important, which we can discard. So here we use the B to stand for the number of necessary mantissa bits. And here we can see compared to a large number, a small number usually has a smaller b. So we prefer compressing the small number rather than the large number, because in this case, a large number of bits can be discarded for high compression ratio. And we also make the following 3 observations of the necessary mantissa bits. B. So first, B is strongly dependent on the exponent part. And next, B becomes smaller when the error bound becomes larger. And in this case, the compression ratio becomes higher. And the last, the B becomes larger when the floating point value becomes larger. And in this case, the compression ratio becomes lower. And this is the algorithm of the bitwise compression scheme. So the difference from the bitwise compression is we use the bit routing. if the data cannot be predicted. And here we use 3 bits to express the linear prediction. And here the leading bit 1 means this is a linear prediction data. And here the leading bit 0 means this is a bit routing result. So, so we do not use any displacement information like in the bitewise compression. So the overhead can be reduced. And this is the MPI implementation of the bitwise compression scheme. And we can see it exchanges smaller amount of MPI messages compared to the bitewise compression because the displacement information are not transferred between the compute nodes. So next, let's make a simple comparison between the bitewise compression and the bitwise compression. So first, in the bitewise compression, because it only does the linear prediction, so its implementation is very simple, and accordingly, the compression speed is very fast. And comparatively, for the bitwise compression, in addition to the linear prediction, it also does the bit routing if the data cannot be predicted. So its implementation is complicated, and accordingly, the compression speed is not so fast. And here the trade-off is that the bitwise compression has a higher compression ratio than the bitwise compression. And later in the evaluation, we can see the bitwise compression usually has a faster execution time than the bitwise compression. So this is the simple comparison between these two proposed compression techniques. So next is the evaluation. Here are the conditions. We use a real machine and several simulations to evaluate the efficiency of the proposed lossy compression techniques. And here are the MPI applications we use in the evaluation. And in these error tolerant applications, and the floating point data are transferred between the compute node. We compress the data on the sender side and decompress them on the receiver side. And next, this is the result of the compression efficiency. We set different error bounds and use lossless and SZ as the competitors, and they are the state-of-the-art compression techniques, but used for the storage systems. And the SZ is not applicable to the inter-process communication. So here is used as a reference. And from the result, we can see the linear prediction plays an important role due to its high compression ratio. And the first 3 linear predictions, I mean the n is 0, 1, 2, contribute much to the compression ratio. And during the compression, we maintained the error bound for each data prediction. However, we know that the error may compound via the compression of consecutive data pieces. So from this table, we can see the final compound error can be still maintained even if we use different error bounds. And here we can see for the compression time and the decompression time, the proposed lossy compression techniques shows the advantage over the SZ, which is the state-of-art compression technique. Next is the result on the real machine. For these different MPI applications, the proposed lossy compression techniques show the advantage in terms of compression ratio and the execution time. And here is the error of the k-means clustering result by using the proposed lossy compression techniques. And here we can see the proposed lossy compression can generate almost the same pattern as the uncompressed clustering result. Here, the same color shows the same cluster in the clustering result. And here, the clustering error will happen after the error bound jumps over a large value like this. And here are the results of the simulation on 64 compute nodes. And these results are consistent with the result of the evaluation on the real machine. And next, this shows the result of the throughput and the latency by using different compression ratios. And this shows a high compression ratio can improve both communication latency and the network throughput. And this is the general purpose evaluation for the proposed compression algorithms. So finally, let's come to the conclusion. So in this work, we propose a lossy error-bounded floating point data compression technique on interconnection networks. And the existing data compression techniques usually target the storage systems. So to the best of our knowledge, this is the first work to apply the data compression technique to the interconnection networks. And our algorithm allows some errors to substantially reduce the communication overhead and speed up the execution. And also we get the better balance between the overhead and the compression ratio. And by the evaluation, we get the improvement in terms of the compression ratio and the speed up by using some typical MPI applications. So finally, the conclusion is that we highly recommend using the application level lossy compression like the bitwise compression on interconnection networks. So this is the end of my presentation. Thank you.